designing systems, reading data sheets, writing software, and rewiring my hardware to make products. An introduction to embedded systems needs to start near the beginning. So let's start with the definition. Embedded systems are things that run software but aren't computers. If you're already an embedded software engineer, you know this. In fact, this talk isn't going to teach you much new. The topics I touch on, you probably deal with on a weekly or monthly basis. But the introduction presentation isn't really intended for folks who are already in the industry. It's for a software engineer who gets handed a project, maybe a tech lead or a manager who used to be a software engineer, and this project that got handled, well, suddenly they need to develop an embedded system. Usually this happens because its normal caretaker isn't available. So it gets turned to software because it looks like programming. This poor engineer, now scratching her head, trying to wrap her mind around the whole system. She keeps asking, why did they do it this way? And were they idiots who didn't understand encapsulation and testing? And how did they let the schedule get so far behind? Well, back to this slide. What is an embedded system? As I go through the presentation, I will give you different definitions, but let me try to start with something more reasonable. It's a bit tricky because embedded systems are different things to different people. To someone who's been working on servers, writing an application for a phone app, well, that may feel like an embedded system, but to someone who has been working on 8-bit microprocessors, anything with an operating system doesn't seem very embedded. I try to tell non-technical people that embedded systems are things like microwaves and automobiles that run software but aren't computers. Most people recognize a computer as a general purpose device, but that just shifts the definition into some other amorphous blob. So let's try this one for a while. An embedded system is a computerized system that is purpose-built for its application. It lacks pizzazz, but it covers the highlights. Instead of being a general purpose system, an embedded system is streamlined to do what it needs to do. And that streamlining can take a toll, mostly on the engineers who build the refrigerators, satellites, and smartphones. Here's the first big thing you need to know about embedded software engineers. They probably started out as a software engineer who kept getting deeper and deeper into the depths of the system, or as a hardware engineer who liked to fiddle with the software. Their educational background is either computer science, like the books on the left, or electrical engineering, like the books on the right. But embedded software is a combination of the two. A new embedded systems engineer is cruising around with only half the knowledge they need, only one discipline when they need both. And there's been a fair amount of talk about imposter syndrome in engineering, where it feels like a person doesn't belong. They're pretty sure they'll be found out and ostracized. And I think this is worse for embedded software engineers because it's sort of true. Until you can pick up the basics of the other discipline, you're walking around with only half the information you need. And there'll always be gaps. And that's why some of my best friends are hardware engineers. They've helped me fill in the gaps. So piece of advice number one, even though electrical engineers seem to be from another planet, make friends with one or two. Most of them seem to like lunch. Then when you ask them to explain this mess, you'll have a slightly better shot of getting a good answer. This is a schematic. It represents hardware. It describes each component and how they're put together. To be able to use a board, you'll probably need this schematic, partially for those connections, but also because it tells you detailed information about the processor you're going to use. Learning to read a schematic seems daunting, but it's one of the easiest things you'll need to learn. Once you get past the impossibly tiny font, and all the extraneous components, it's like a block diagram. like a system or a software block diagram with lots of extra squiggly lines. In general, the bigger the component is on the schematic, the more likely it will be important to the software. So if you have to puzzle out a schematic on your own, start with the big boxes. Google the numbers in and around those components. And be patient with yourself about all the little ones that you don't recognize. So take the schematic. You don't really need to read it. But the biggest thing on it is the processor towards the middle bottom. The tiny script at the bottom reads ATMEGA 328P-PU. What a nonsensical name. I'm glad they're not responsible for naming my software variables. But there's a lot of information coded into that name. The ATmega, ATmega, ATmega family of chips are all sold by Microchip. But originally they were sold by Atmel, which is where the AT comes from. Isn't it great to have to know the history of what you're doing as well as actually getting things done? But the 328 describes their most popular chip, the one used in the Arduino Uno board. Those numbers also describe the flash and RAM sizes of the particular processor that should be used in creating this board. After the dash, those letters describe how the chip is packaged and put on the board. They don't generally matter to you as a software engineer, but a schematic also provides people a list of parts necessary to build the boards. And I've been saying processor, but you might have heard microprocessor or DSP or microcontroller. These all have slightly different definitions, but the definitions change. So I will stick to using processor or chip. When I say that, I mean the part that runs the software you will be writing. And whatever terminology you use for it, you need to know what the processor is, the vendor and that mix of letters and numbers that describes the chip. You'll need that information for when you go to look for the documentation associated with the processor. Start by looking at the processor's Getting Started guide. That'll tell you about the basics of the build system, such as where to get a compiler. It will walk you through a hello world-like example, usually involving blinking lights. And the Getting Started guide will provide you with some example code. It may tell you where there is more. Don't get lost in the processor datasheet. Those are usually things for electrical engineers. And the software needs to know some of it, but it will all be replicated in the user manual. So after you find the Getting Started guide, the next thing is the processor user manual. And that's where all the good stuff is. This is a snippet of a processor user manual from the section that describes how to talk to the processor's GPIO or general purpose IO subsystem. You communicate to this part of the processor using registers. Registers are like a software API. They tell the processor what you want to do, but like software APIs, you have to talk to them in the way that they want. This snippet is from the middle of the manual, the top one, this top snippet. And so I have made it a little difficult for you, but don't worry, I'm actually going to torture you for a few minutes with more information about registers and how to use them. See, I want you to understand that I'm giving you the surface view of embedded systems. This is the introduction to embedded systems. I want to give you the confidence to talk to embedded software engineers, but I don't want you to get overconfident. I also want to show you how registers and processors aren't exactly like software APIs, unless you've been using some pretty finicky APIs. As you get to know your new processor, expect it will take almost as much effort to learn as if you were learning a whole new programming language, a weird programming language. As with learning the language, if you've already worked with a particular processor or something similar, it will be easier to learn a new one. And as you learn several programming languages or processors, you'll find that learning new ones will become easier and easier. Although this metaphor gives you the idea of the scale of the information you'll need to assimilate, remember the processor itself is more like a large library with an odd interface. Registers are that interface. They give you a way to talk to the processor. Say you want a pin on the processor to be high. Maybe you want an LED to be turned on. So you set the pin to be an output, which I haven't shown here. And then you set the pin to be on or high or 1 or true. These registers are memory mapped, so you can write to a specific address to modify the registers, as is shown on the bottom of the slide. However, don't do that. That code is just as hideously ugly to us C programmers as it is to anyone else. The processor vendor almost always provides a memory map of the chip so that you can, use these registers as global variables or as part of a structure. These are part of the hardware abstraction layer. Usually it's more than simply a header. Sometimes it's a whole set of libraries. Note that the register names are different for each processor, but the effect of the code is the same. In each line, it is setting the second bit in the byte or word. Each of these registers is both read and write, but some processors have write-only registers and read-only registers. It's kind of like a const keyword in a programming language. And there's a good reason for it. It has to do with atomic actions and things that shouldn't take 2 steps. But these here are read-write registers, and we're setting the second bit. Your system will probably be written in C, or maybe a non-modern version of C++, possibly with pieces of assembly that you hopefully will never need to look at. There are other programming languages that are used in embedded systems, but if you are seeing a lot of them, it's likely to be C or C++. And if you're accustomed to a language with garbage collection or one with built-in dictionary types, you may be in for a bit of a shock. It'd be like going from driving around a nice car you bought in the last year or two to a 1984 Honda Accord with starter engine trouble. It's even more difficult to get thrown into a project when you need to learn both the processor and the language. And I'm not sure what to tell you about this. Except to recognize the learning curve is quite steep, and it's not you. There are lots of good C books out there, and there'll be example code for your processor. And if you've used C++, even then, you may not have worked much with bit manipulation, which is shown here on the slide. You need to remember all about binary numbers, and then bitwise operations. These are like logical and, or, and not. But instead of working on the whole variable, they work on bits inside the variable. I've been showing those with the register change on the previous slide. Where the logical and has 2 ampersands, the bitwise and only has 1. Same for or with the pipe character. As for not, instead of an exclamation point, bitwise not uses a tilde, and it reverses every bit so the 1s become 0s and the 0s become 1s. I can hear your eyes glazing over, so I'll cut this short. All of this is just information. You can get it from Wikipedia or a book. It may be new to you, but it isn't magic. I'm happy to work with bit manipulation and hexadecimal numbers because they make registers easier to understand. But that's born of experience. It used to give me headaches too. Software and embedded software share commonalities, but they are different. And I wanted to get detailed on this concept. So you see that things go pretty far down. It isn't just surface levels. And I chose registers and bit manipulation because it's one thing you may have to deal with early in your embedded software career. And I have one more slide in which we'll continue our deep dive, and then we'll go back to a little bit higher level and more tactical subjects. No, sorry, more strategic subjects. This is the tactical one. This is something every embedded programmer should know, the keyword volatile. It's most likely to be brought up in your embedded software engineering interview. It's available in C and C++ and Java and other languages. If you were to write this snippet of code without the volatile keyword, the compiler could optimize out the reset of this line. Now, let's pretend we are the compiler for a moment, looking at this high-level language and translating it to some low-level language. We go through, we see the variable gets set to a register. We know how to do that. Register gets set to a value, okay. And then we call a function that doesn't affect the register, that doesn't affect our variable, and then our variable changes again. But wait, why did we change the variable twice? We're a smart compiler, we can optimize. Let's just change the variable to the end value and after the function call. That's not going to work here because the register has side effects in the processor. The volatile keyword tells the compiler that the value of the variable may change unexpectedly, that it should not be optimized out. All registers should be marked volatile because they come from the processor. And while I'm not going to talk about interrupts at all, global variables that are shared between interrupts and normal code should also be marked as volatile. But let's go back to the higher level of embedded systems, stopping along the way to talk about hardware and bugs, which is to say hardware can have bugs. When I write software, if something goes wrong, I have only myself to blame. The compiler is usually rock solid, whether I'm using GCC, Microsoft Visual Studio, Xcode. I'm pretty confident that any incorrect behavior on the part of the software is my code. It's my mistake. It's something I did in programming. However, in embedded software, the bug could be my software. It could be the hardware, which may have errors in design. The board, which may have an error in manufacturing, like a solder glob or a loose wire in a connector, or a piece of dust that landed on my board overnight. It may be a power supply that's failing, a processor with a known bug, but I haven't looked up the errata lately, a compiler that was really designed for assembly and not these fancy C++ features. It may be my software, or it may not. Bugs are not solely in the software engineer's domain anymore. The uncertainty at every step is difficult. Some might say maddening. It may be what drives embedded software engineers insane. No, wait, of course not. Now that I have enough experience and I know enough about hardware, I can start with the idea that bugs are software and then build a case for them to be hardware or in the tools. However, before I got this far, I was pretty powerless to find where the bug was. It's too easy to throw bugs over the engineering wall and blame it all on hardware. No one likes to be wrong, especially when they really are. Saying there's a bug on the board isn't the best way to start a conversation. On the other hand, most people like to help. So ask for it. Remember the hardware engineer you've been lunching with? Now is the time to buy lunch and ask for a bit of his time. I've had great hardware engineers who would sit with me and listen to the problem and take the time to help me. Maybe by modifying the board so I can see the problem in a different way. They don't get cranky when it's just a software issue because I don't get cranky when it's a hardware issue. Instead, when it's hardware, I write tests, help them identify the issue or identify the issue on new boards. Remember, embedded engineering is a team sport and it's an interdisciplinary team. Okay, next fact about embedded systems. Many embedded systems are poorly written. Oh, wait, was I supposed to refute that? No, there's a reason why, though. Not only is there the issue with knowing only half the discipline, there's a problem with the schedule. This schedule is idealized, not important if you can't read the details. In the beginning, there's requirements gathering, then hardware and software get started building things, tra-la-laing through the forest, and at the end, everything releases on time. Yeah, I know it never happens like that. However, the idea that hardware needs to be done before software can be finished is what's important here. If the hardware is delayed and the product has to ship on time, maybe because it has to be on shelves for Christmas, guess what gets squeezed? If there's a quality department, realistically, they're the ones who bear the brunt of it. But what they're doing is testing the software. So If quality it gets cut short verifying the software, the system will be buggier. And sometimes the bugs are in the hardware, but there isn't time to do a hardware spin. So instead, we create a software workaround because it's cheaper and faster to do it in software, even if it requires some horrific contortions that leave the software unable to implement future features that seemed important at the time. For example, I worked on one project where we were supposed to have external memory to help with updating firmware in the field. When the external memory got flipped around in the hardware manufacturing, they couldn't fix the boards that had already been manufactured. So we did firmware updates in a way that was much more dangerous to the system if it was powered off. And we didn't have much time to test the new loading mechanism because we didn't know we needed it until we got the boards back and the memory didn't work. The project worked out, but I still cringe when I think about that code and the chances we took, the risks we added because the hardware didn't come up the right way. In a schedule like this one, it looks like software has a big chunk sort of towards the beginning where they can have time to read manuals, to work on good design and write software, even without the hardware, even with, dev kits. Kind of, although that time doesn't always exist because of the firefighting on the previous project. And if it did, writing software for an embedded system without hardware is like writing a long program and waiting to compile it until it's all ready. Embedded software needs to run on its hardware at least at some point in the schedule and not the day before it's supposed to ship. The software development and debugging time gets compressed when things go badly in the hardware design and manufacturing stages. This is just the nature of the business. There's so much, there's just not much you can do to change it, except one thing. That is all the free time in the schedule can be used to create hardware tests that can be used to verify things in manufacturing and during board bring-up. Though that goes back to you thinking about you as a software engineer that may not have been part of the whole process. Let's go back to the idea that you just started this project, that you just got assigned this embedded system, possibly against your will, and you have the hardware and you want to run some software. I promised more definitions of embedded systems. And here's a good one. They use cross compilers. Cross compiler runs on your desktop or laptop computer, but it creates code that does not run on your computer. Instead, that image runs on your target processor. These compilers are sometimes quite expensive and provided by the processor vendor or a third party that works closely with the processor vendor to get all of the pieces right so that this is easy for you to do. Compilers may also be free, a GCC variant that you simply need to set up properly, something that can be much harder than it sounds. If you want to debug software running on a computer, you could compile and debug on the computer. The system would have plenty of resources to run the program and support debugging at the same time. In fact, the hardware your computer, it wouldn't even know you were debugging an application. That's all just software. Embedded systems aren't like that. In addition to cross compilers, we have cross debuggers. The debugger is a piece of software on your computer, and partly it is a physical device that sits between your computer and your target. It communicates between the target and your computer through a special interface dedicated to letting you eavesdrop on your processor. The interface and the debugger hardware are often called JTAG. Whether they actually implement that particular standard or not, expect to hear the word JTAG. The embedded processor must expend some of its resources to support this debug interface, allowing the debugger to halt it as it's running, and providing the normal sorts of debugging information like call stacks and variable values. Supporting debugging operations adds costs to the processor. To keep the costs down, the processor supports a limited subset of features. For example, adding a breakpoint causes the processor to modify the memory mapped code, memory loaded code, to say stop here. So you put in a breakpoint, and as it goes through, the code will be modified to say stop here. However, if your code is executing out of flash, out of or any other sort of read-only memory, instead of modifying the code to say stop here, the processor has to set an internal register, a hardware breakpoint, and compare it at each execution cycle to the address being run. And when they match, it will stop. Are you there yet? Are you there yet? Are you there yet? Oh, let's stop here. This can change the timing of the code, leading to annoying bugs that occur when you are or maybe aren't debugging. And internal registers take up space. They take up resources. So often there are only a limited number of breakpoints. Frequently, there are only 2 hardware breakpoints. What can you do with 2 breakpoints? Quite a lot, actually. But it can make debugging the software feel like playing Tetris at level 10. To sum up, embedded processors support debugging, but not always as much debugging as you're accustomed to. However, how will you make your software debuggable in a somewhat hostile environment? It can be tricky to balance the needs of the programmer and the constraints of the hardware. And with a debugger that is somewhat weak, we resort to printf. However, as an embedded system often has to do things quickly or react to an input in a very small but specified amount of time, which is called real time, printf can cause problems by changing the timing of the system. Kind of like the uncertainty principle, Heisenberg. If you can't always run what you want and be able to see what you're running at the same time. See previous mention about debugging being like playing Tetris. And I say printf, but what I mean is output through a serial port. Serial ports are common embedded systems because they are so very cheap to add to the hardware. And some might say we can decrease our reliance on hardware and software debugging, or on hardware and printf debugging, by doing better software tests. And I agree. That time I mentioned earlier in the schedule when I'm waiting for hardware to finally arrive, that's when I write a lot of hardware bring-up tests. And I like unit tests. And I like breaking up an application so that the algorithm can run on a PC with canned data, so I don't have to work on my hardware all the time. Of course, if the computer is 64-bit and the embedded processor is 16-bit, that can introduce its own set of bugs. And how do you identify which pieces should be tested where? If you want to test on the hardware, you can build a widget to inject signals into the communication path, like the SPI wires on the slide. But then you have to debug the widget, which is probably a separate board and processor and a whole nother embedded system. It isn't that embedded software engineers don't test their code, but there are so many places where we can test it, and we can often only test pieces of it at a time. The more thorough the testing, the longer it will take. And how much do you really want to simulate the hardware? How exact should the simulation be? Where should those unit tests run? On your computer or on the chip? I won't make excuses for people who fail to write good tests. We especially need ones that verify the hardware is functional, because everything else we can deal with in software. But remember what I said about the schedule. Embedded software ends up being crunched for time, needing hardware but waiting for it, and then trying to build a complete system without very good debugging tools. The existence of the schedule pressure is the same in general software, of course, but the details are quite a bit different, which leads to testing happening in different ways. And sometimes the system is more than one embedded device. When you add in networks, well, systems get complicated fast. Isolating the problem can become the hardest part of debugging. I recently had a project that had Bluetooth audio. And between the audio going through multiple pieces of hardware, a half dozen audio processing subsystems, and then through the air to a system that was almost but not quite its mirror, trying to find which of these pieces was misbehaving became the trick. I spent a lot of time drawing it all out into little block diagrams so I could isolate and verify the parts of the system. I encourage this type of decomposition for better understanding of the devices and their layers. A drawing like this is also a good tool for architecting a system, helping you design for encapsulation and testability. But that architecture was probably settled before you got saddled with this project. It'll take a while to shift towards testability and processes that work for the whole team. Let's get back to the idea you've been given an embedded project to babysit. Here are some tactical questions to ask when things go wrong. You'd be surprised how many bugs can be solved by slowing down and verifying that the system is powered. And not only the whole system, but the peripheral causing the problems. And because the system uses a cross compiler and the code needs to be loaded in a separate step, usually a manual step, there are plenty of times the bug doesn't get fixed because the system isn't running the code you intended. These seem like obvious, simple things, but smart people get tripped up on commonplace details. Check the easy things first. These are some questions you can ask when things go wrong, and I'm a huge fan of talking through the problem. Many issues can be solved by laying out what you expect versus what is actually happening. Rubber duck debugging is mighty effective. And I mentioned earlier about not having enough resources when debugging. But not having enough oomph is another characteristic of what makes a system embedded. I gave a bland definition at the start. An embedded system is a computerized system that is purpose-built for its application. Because its mission is narrower than a general-purpose computer, an embedded system has less support for things that are unrelated to accomplishing the job at hand. The hardware often has constraints. Consider a CPU that runs more slowly to save battery power, or a system that uses less memory so it can be manufactured more cheaply, or processors that only come in certain speeds with certain peripherals. This slide shows the big shows this slide shows the big resources, and you may hear about trading them, exchanging one for another. To some extent, an application that uses more RAM or code space can ease problems with the speed of the processor. Alternatively, if there isn't enough code space, the processor may have to do more to calculate things on the fly instead of having them be stored in the code. And this sort of optimization is difficult, more of an advanced topic in embedded systems. So I'm only going to give an overview. However, before we even start that, it's important to check the cost benefit analysis of optimizing embedded software. There's a good reason our processors keep getting larger and larger, and it's not necessarily because we're doing more with them. It's because optimization is hard. Once a function is identified as slow and written in hand-tuned assembly to make it faster, no one will ever want to change that function again. It will be easier to rewrite than to read. Once RAM is optimized so that it's shared between two modules, the encapsulation is forever damaged, and changing either module may break both. And when you run out of code space, a single small bug may require you to change code in 15 locations to make space for the fix. When you ask an embedded software engineer why they did something, and they reply, "That's how it's always been done," that may be a cop-out, but it also may be an important state about the fragility of a system that's been optimized to work with the resources available to it. So when we talk about optimization, speed, let's start with the speed of the system. Processing speed comes in different shapes and sizes. It isn't just about clock speed. Sometimes you can't get a processor that has all the other features you need and runs as fast as you want. Processing power also depends on other parts of the hardware, such as how long it takes to access memory, whether the hardware has a method for storing data quickly as it comes from or goes to a peripheral. The size of the registers is also important. 32 bits at the same speed is going to be faster than 8 bits. Speed also gets limited in different ways. Slower clocks consume less power. That means you'll need to optimize the code to get more done in fewer cycles to make your wearable battery last longer. Or you may have a system that skimps on processing power because slower processors are generally cheaper. Less memory also makes for a cheaper and more power efficient system. Not having enough RAM can be a big shock to software engineers, but it can be a neat puzzle to implement a complex algorithm in small steps using snippets of data instead of a huge chunk in post-processing it. And I've heard people squawk, "What do you mean you don't use dynamic memory allocation?" Well, New and Malak use RAM in their implementation. And when you're counting bytes, you need those bytes. And you need to know where all of the other bytes are going to. And the way to do that is to allocate everything at compile time. I suppose you first need to understand where the memory is, such as the memory map from this processor manual. The first megabyte shown here isn't real. It's just address space. It's address space that impersonates another address. Then there's 1 megabyte for internal flash. This is code space, and 1 megabyte for RAM. However, those address spaces don't really exist. The actual chip you can buy, the one I took this address map from, only has 256K of flash available and 32K of RAM. It's about enough RAM for 2 seconds of MP3 audio. And there are many techniques for optimizing RAM, but one of the most popular is to have a large chunk shared between 2 modules or objects. And sometimes the 2 pieces of code need the same data, but copying the data is slow and you don't have enough RAM anyway. More often, the 2 modules trash each other's data, taking turns using the RAM. And as long as everyone is polite, it works out fine. But odd bugs happen when both modules write to the buffer at the same time, interleaving their data with predictably disastrous results. I'm going to quietly back away from that mess, and you probably should too. But one thing to note here on the slide as we look at the addresses without memory and addresses that can be remapped onto other addresses. Embedded software engineers deal with pointers very closely. Not only is RAM sometimes a precious resource, memory is a very real physical resource. Pointers to memory aren't amorphous blobs. They point to specific chunks in the hardware, specific memory chunks in the hardware. And those registers from earlier that were memory mapped, as though they were pointers to memory or pointers to pieces of the hardware itself, pieces of the processor itself. Let's go into code space. Now, I mentioned having 256K of code space, which is non-volatile, which means it remains constant through power cycle. RAM does not usually. More specifically, the 256K of code space was flash, which is really a common type of memory. It can be reprogrammed, but it isn't easily reprogrammed like RAM is. It's closer to read-only memory. Some projects still use true read-only memory, but those are usually for over 1 million item consumer products. 256K of code space seems like a perfectly reasonable amount. But then I've worked on projects that had 32K, packing data and algorithms like sardines into a too small can. And when you need to do this type of optimization, when you need to consider what is happening, really happening in RAM and code space, the file to look in is the memory map. The output the memory map is an output of the build system that says where it actually puts all of the variables and functions that you created. The files are hideously ugly, but sometimes they provide the only way to truly understand how the code is functioning on the hardware. There are other files you may need to dig into, files you've never seen before. Linker files describe how you want the memory map to be. Assembly files that cover how the system starts up before you ever get to main. And list files that describe what your code looks like to the processor. But I'm close to out of time, and that is why I wrote a book, to explain things like that to folks like you. So as you think up more questions for me, I see we have a few already. I want to say thank you for attending. I've enjoyed putting together this presentation. I hope you've enjoyed listening. And while I don't generally like to have too many slides, too many words on my slides, there were no simple icons to describe the big points I want you to take away today. I suppose it could be summed up as I hope you feel a little bit more comfortable with embedded systems and embedded software engineers. And for all that I have told you how hard it can be, embedded systems can be really fun too. I don't want to discourage you. Making a gadget that does something, even as simple as blinking a light, or seeing something you've helped build on a store's shelves, it's an amazing feeling. The code we write changes the physical world around us. And the work itself is interesting. The puzzle aspect of coding has always been my favorite part. In embedded systems, there's a few more dimensions to that puzzle. I do want to thank O'Reilly for putting this on for us. And now let's see if there are questions about the material I've presented here. Jenny, do you want to ask me these questions, or do you want me to try to parse them?
Let's see, what do we got here? We have Mark. What are the prerequisite knowledge required to start learning about the developing embedded systems? Do you want to take that one?
Sure. Although I note that it was asked at the beginning of the presentation. I feel like I've somewhat
Covered it
that.
since then? Yeah, okay. Could you also recommend from where to learn those prerequisites? You did address this, yeah. Could you provide a flow chart for a path to get into this field? I gave it basic programming skills, but no electronics. Do you have anything more to add to that, Elecia?
I do. Let me I do have something for you, Mark. I'm going to drop a link into the chat, I think is the way to go. I don't know if I can if there's a better way to give you. So one of the things that I have is this embedded skills tree. This is the flow chart for a path to get into the field. You start at the bottom and you go up. You don't need to do all of these things, but it gives you a list of tasks. Can I share this window as well? Let's go with no. So take a look at that. That might help you identify some skills that you have and some skills that are next up on the list. Follow a path is interesting. And I like projects if you aren't already in the field, because it gives you something to talk about when you're interviewing. And I can talk more about that, but let's see if there are more questions.
What are some of the books or online courses you recommend? Is there a 0 to hero type of a program?
Well, let's see. I have my book and I recommend that. And of course, I don't know of any 0 to hero type programs. I was teaching a course for a little while myself, but it turns out I really prefer engineering. There are some Coursera courses that are quite good, but of course it means you have to be very self-motivated. I don't think there's a 0 to hero course. I know there are many books, and Grenning and Koopman are both great authors.
Okay, let's see. Will the coral be running again if we used your book exclusively to build practice systems, which would much more be gained from the course as well? Do you run a course?
I was running a course for a little while,
Okay.
but no, like I said, I really prefer engineering. It took me a while to
Yeah.
understand that teaching is its own thing, and I enjoy preparing these lectures, and I enjoy giving them once. And
Yeah.
then after that, I'm not a teacher. I like to think about how people learn, but then once I'm done, I don't want to do the performance each time.
Understood. Okay, here's another one. In your experience, is using emulators a good way to develop and test, or too much of a headache to make it worth it?
Um, there is one uh, simulator actually, that I strongly encourage people to take a look at, and that is Walkwe. The person who does it has created a whole bunch of boards and simulators and systems, and they run a simulator of the processor. So it's very close to what really happens. Things run a little bit more slowly, but you can do all of the bad things. You can let the smoke out of the simulated board because nobody cares. Um, and it is a fantastic emulator. Overall, it depends on what you're doing, and it depends on what you mean by emulator. Many, many times I have created sandboxes where the algorithms run in on the computer and emulate some portion of the hardware, but usually through files, through reading and writing files, and then we can retest that part of the algorithm. If you're doing big displays, uh, Qt uh, has a fantastic emulator, but at some point you have to put it on the hardware. You can't avoid that because there are always discrepancies. And so you have to balance the idea that you will have these discrepancies and they may bite you um, with the emulator. So make sure you don't just use one or the other. And what is the difference between a simulator and an emulator? That question used to have a really good answer. A simulator runs entirely on your computer. An emulator may run on different hardware. But these days, our emulators also run on our computers. So I'm not a simulator. A simulator may not do the same thing on the back end. An emulator should have the same sort of features that implement each step. Now, if you think about that all the way down, at some point the emulator isn't the same as what your goal device is. So it can't be emulated all the way down. But it used to be emulators were pieces of hardware and simulators were pieces of software. Now, I don't think the terms have as much differentiation as they used to.
Okay, let's see. What else do we have? What are the merits of building embedded software from scratch versus using boilerplate HAL libraries provided by silicon vendor tools?
Well, if you want to learn things down to the ground, building embedded software from scratch is very interesting and useful. But if you want to ship software, if you want to ship hardware, if you want to actually get things done, then use the HAL libraries. They may be slightly slower than what you could build yourself, but the speed gain you get from having it all be done and tested is 100% worth it. So use the HAL libraries. If something needs to go faster or needs to be optimized, deal with it then. Don't write that code from scratch. It's not worth it. And HAL is hardware abstraction layer because I didn't do a good job of starting that one.
Thank you. Um, let's see. Is it always necessary to debug embedded system using physical tools rather than using the software and serial monitor?
So the serial monitor, I talked a little bit about printf debugging. There are projects that can be debugged and entirely through printf debugging. But if you run into a problem that can't be solved that way, can't be solved that way because it deals with an interrupt or some tweaky part of timing that the serial monitor affects. I have worked on printf only debug projects. Absolutely. There were a line of boards for a while, the embed boards, and you could do a lot with them. But yeah, I see in the comments, not on real-time systems, not on robots. There's a lot of times where printf debugging is not sufficient. And it usually does have to do with having functions that need to respond in a very short amount of time, where printf is not enough and where you need to debug things that are happening deep inside the chip. So I'm going to go with you can do printf debugging as long as you have a processor that doesn't need to be truly optimized for anything.
Thank you. Let's see. Where should we go from here? When debugging, how do you go about isolating whether a bug is caused by the chip, peripheral, or the SW design?
The software design.
Thank you.
How do you isolate where the bug is? Well, I had this slide, the debugging slide. There are two ways I go about debugging. On one side, I try to figure out how to reproduce it, how to reproduce a bug so I can get it to happen on command with the minimal amount of code. On the other side, I try to explain the bug. So there's reproducing it and explaining it. And in reproducing it, it's all about minimizing it and trying it. And explaining the bug, it's all about trying to figure out how it could possibly happen and trying to explain to other people about the difference between what you want and what you're getting. So how do I identify where a bug is in the long chain? Well, part of it is minimizing it, and part of it is explaining or reproducing it, and part of it is explaining it. When I explain it, it's about usually drawing pictures, and because that's kind of how my brain works, or just drawing things out. If I have layers, just listing the layers it could be in, and going through and trying to devise tests on how to eliminate each one. So your goal is to get rid of, you start with too big of an idea of what could be wrong. Something is wrong here. Now you go through and say, this part works, this part works, this part works. And this part may work and I don't know how to test it. And that's a big clue as to where the bug may be. The parts where you don't know how to test it. So I think I answered that.
Sounds good. We only have a couple more minutes. I am filtering through all these questions.
The slides are available. Let me.
Yes, and we'll send them in the follow-up email with a link to the recording as well as the slides.
I have a GitHub for the
Oh,
book,
look at you go.
and there's a presentation directory, and these slides are in the presentation directory. If you want to know more about memory maps, which is one of those areas that I find particularly fascinating, I gave a presentation about them called Buried Treasure and Memory Maps, and my link is not linking, but let me get that. Right, I can go somewhere else and get it. It's a presentation that assumes you have already worked quite a bit with embedded systems, but it was really fun. It has an iconic graphic that goes with it that talks about embedded systems. I mentioned Embedded FM, which I keep sending links to. And if you want to try my book, you can do so on the O'Reilly Learning platform. There are 7-day trials and 30-day trials, which again, I could not give you a link for. So maybe Jenny
No
can cough
worries.
up a link for that.
I will cop up a link for that. I put a link to your book in the chat as well. That's on the learning platform. If you would like to have access to not only Alicia's book, but all thousands of other books that we have, as well as other pub partners, please feel free to reach out to us, and we'd be happy to set you up with a trial account, as Alicia mentioned, for you and your teams. Alicia,
Eric,
yeah.
uh, thank you for posting that link, but that book is not intended to be free. I mean, if anyone wants, it's easy to get PDFs of books these days online. And I have no problem if you want to check it out that way. But please realize that if you find a free PDF of either copy, it's not what we intend. Someday that book will be free, but not yet. Not when I put this much effort into it.
Thank you. Let's see. Do you see any in the Q&A? We have, how often do people attempt to convert a piece of software like a database engine, PostSQL, for example, and try to embed it on hardware? Is that an impossible task? Do you have to build an abstraction layer to emulate a full instruction set?
I hope not. Actually, it depends on what you want to do. I mean, if you're just doing this for fun, that's one thing. But I have had software that needed to have databases, and the databases aren't usually PostgreSQL, but something simplified. There are much smaller SQL implementations. Even MySQL can be made pretty small. Do you have to build an abstraction layer to emulate the full instruction set? Again, it depends on what you want to do with it. If you are creating a thumb drive that is also a database, so you can search all kinds of things wherever you are, and you want the freedom to use any type of SQL, that's one thing. If you are creating a bird call identification system and you only need to read out and compare features, that's a different sort of system. So I'm sorry, but the answer is it depends. Let me speed go through these. Shijo, George, a bit about the security side. The S in IoT is for security. Oh, wait, no, it's just one of my favorite jokes, sorry. Security is very important. My answer for security is don't do it yourself. Many of the processor vendors these days, particularly the ones who are doing Bluetooth or Wi-Fi, already have security built into their systems, including the firmware update system. So security is critical. It needs to be built in from the very beginning, and you need to understand what it's doing. But if you can, don't do it yourself. Use existing security methods that are there for your processor. Is system design like UML diagram required for professional advancement? It hasn't been for me. I'm pretty bad at UML. I can sort of read it, but not well. And the stuff that's in my book, I definitely had to look up like each line to make sure I got it right. So feel free to tell me if I didn't. Can you put out a list of all the software tasks done sequentially to use a processor for a project? Where does driver development and operating system come in the sequence of processes? Ooh, that is a big question. So first step, requirements gathering. What do you need the processor to do? How fast do you need to ship the device? How expensive can it be? All of these things go into how you choose a processor and how you choose an operating system. For example, if I want to, I was working on a water monitoring system. And when the client came to me, they described a system that was very small and very, very cheap. And I was, okay, then this is what we need to do. We're looking at this line of processors that are super cheap, but have all the features you need. And it was like I was looking at Cortex M0 pluses, if that makes any sense to you, but small, cheap systems. And they came back a little while later, and I became to I came to understand that what they wanted to do first was to build a system that could be used by scientists to then be optimized down into this little processor system. My version of a Cortex M0 Plus system was not going to work for that, because any change they wanted to make was going to have to go through me, through the code. And so I set them with a Cortex M4, so like much bigger processor, about 4 times the expense. And then we ran MicroPython on it, because the scientists could program in Python. They could make little changes themselves. And MicroPython is big and a little unwieldy for super tiny real-time things, but it was enough because the requirements were very different. So all of the tasks done sequentially to use a processor for a project, task number 1 is you have to figure out what you're building. There isn't a list because it branches right away. How are HAL, hardware abstraction layer, middleware, and firmware different? Ooh, firmware is the easy ones there. It's the odd one out. Firmware is between hardware and software. That's why it's called firmware. Sorry. Firmware and embedded systems are usually the same thing. They're usually the same team. Some people believe firmware should only be applied to things that are basically written in assembly. Fine. I'm not going to use that. That's fine with their definition. Middleware is usually software you get from other people. There were some suggestions about databases that were in the chat. Mongo, or no, Mongo, MC Object. But there's also like fat libraries for accessing drives. Those are middleware. Those are pieces in between. Maybe the piece that runs Bluetooth audio as opposed to Bluetooth itself. The hardware abstraction layer is the very lowest layer. It covers the hardware so that ideally you can change between processors, but realistically, it just covers the very lowest level so that you can say, turn on port A pin 7 instead of writing to a horrible address or even writing to a structure. So the HAL is at the very bottom. The middleware are the libraries and things that use the HAL, but also add features to it and are primarily software-based. And firmware is the whole thing. Okay, will this presentation be available as recording? Yes, it looks like we cut off the first couple minutes. I'm sorry, I didn't remember, Jenny.
Sorry, me either. My apologies. This is Elecia White.
I have a podcast.
Yes, check out the podcast. It is fabulous.
If you do enjoy this presentation, there's the book, of the podcast, the slides. What else do we have on the slide? And there's your Riley Learning Center. Oh, I put all of those up there. I should have showed this. And then there was a question about what's new in the second edition. Interrupts, the whole chicken thing. If you've read the first one and you like the Triceratops, you'll probably like the chicken. I like the chicken a lot. Managing the flow of activity, the whole, how do you set up your main loop? Do you use polling? Do you use interrupts? Do you use active objects and state machines? So that whole part. Getting into trouble, which is all about debugging. I mentioned the whole explain things and reproduce things. That's all in there. And then motors and movement went into their own chapter. And then there are a couple other things that changed. There was a section about bootloaders and how they work. That was a chapter, and now it's a section into the whole IoT and how to manage your devices and how to think about them. So that's what's new in the second edition. Can one develop embedded software in an agile manner? Yes, of course. But just remember you have hardware in there. If the hardware is coming in at certain times, then you can't expect your agile software team to do things without the hardware. And since hardware isn't something that happens on week or 2 week schedules, that's sometimes a little difficult. If you have most of the hardware available, then developing embedded software in an agile manner makes a lot of sense, especially the unit test sides and the story sides, and making sure things are integrated and tested often. That's all great. But asking me to finish my code when I don't have hardware, I can finish a prototype of my code, but until I have hardware, it's just that. Machine learning, there's a new section in the book about machine learning. I didn't put it on the slide. I think it's cool. I am skeptical, but I think it's cool. But I'm really skeptical. There are lots of new processors coming out that have machine learning features built into them. But I grew up using, I grew up using heuristics and algorithms and time-tested things and putting it all into a chip that I don't know how it's going to respond, and I can't explain why it does this versus that. I wrote a fairly successful self-driving vehicle code. So I've seen how powerful it is, but when things went wrong and I couldn't figure out why, no one could figure out why. I wrote it. If I couldn't figure out why, nobody could. And things shouldn't depend on the time of day. Okay, AI is probably not where we want to go because I could just waffle about that forever. TDD approach of development rather than traditional way. I think that works great for some people, and for other people, it's too much simulation. And test-driven development is a really good way to teach yourself to think about how can I test this as you are developing it. Instead of just writing the function, minimum of 2 numbers, you write a test that fails. And then you write your test of minimum of 2 numbers, or you write your function, and then you write a test then your test should succeed. You write some more tests to see that all of the things should succeed. It's really good to think about how things should be tested, how they can be tested. But I don't use it for production because it can be a bit clunky. It runs on my processor, or it runs on my computer, and that means that sometimes my processor feels like it's been tested, but it hasn't. My processor code. So I strongly encourage learning TDD, and I am agnostic as to whether or not you should use it for your production software. I personally am not a huge fan of doing it for production software, but I've worked in places where they did it and it was cool. So whatever works for you. Can you recommend a friendly place for beginners and intermediates like us to hang out and share our learnings and questions and help each other? Wayne, are you already? Okay, so I have the podcast. Podcast has a Slack group. Slack group costs $1 to join from Patreon or Coffee. It's pretty cool. But if you don't want that, the Adafruit Slack is really fantastic. MicroPython Slack is very good if you are interested in a MicroPython. Zephyr Slack, if you are thinking about using operating systems and want to get into that. I don't have a good answer for you. But if you email the show, which is show@embedded.fm, we will cover that on an episode. Memfault Slack, Discords. I can't change my Discord right now. But yes, there are many places. And some of them, it's personality. Some people like to be more abrasive, and some people like to be helped. Adafruit is Discord. So is MicroPython. Interrupt from Memfault is Slack. Yes, Memfault Slack. Thank you. Okay, we are almost out of time. Do you use oscilloscopes, digital microscopes? I have a microscope, analog microscope. I have a logic analyzer that is plugged in and in constant use on my desk. I have an oscilloscope that sits on my shelf that I don't use nearly as often. I have a voltmeter underneath my desk, magnetized so that it sits within easy reach of my left hand. I have multiple JTAG systems because I'm a consultant. And so who needs what JTAG depends on what processor. I've got ones for PIX and Cortex and TI DSPs and various ones. But yes, I think that if you are only going to buy one tool, you should buy the logic analyzer that is at the middle top of your price range. And the middle top of your price range can be $20 US. Because there are some ones that run for that and they're not great, but they're better than what you have now, which is nothing. Agile. Do I need to be concerned about not being from CS as you come from EE, an early career engineer? No, I mean, I kind of geared this presentation more for the CS side, but electrical engineering, instead of worrying about wires and schematics, you're going to have to learn more about software and how software can be used to make things much better. You're going to need to learn about patterns, design patterns, so that you don't implement software that is just what you come up with the first time. Design patterns are the idea that other people have seen these problems and they've come up with good solutions. And they may not be the perfect solution, but they're good solutions. And so there's a whole bunch of design patterns out there that solve very common problems. And as an EE, you probably have not seen a lot of design patterns. You haven't seen a lot of data abstraction, which is sort of a design pattern that says, look, I don't want to have to deal with if else a billion times. Instead, I'm just going to put it all in a neat data packet and it will sort itself out. So coming from an EE side, you want to learn more about CS. My book, the intention is that you know about half of it. That some of it is CS that you're learning and some of it is EE as you're learning. It depends on which side you come from. This is the goal, to bridge the gap. All right, I'm about done answering questions because I need to get something much.
I want to thank you so much, Elecia, for your time today and your additional time for all these questions. I see all these chats coming through of everyone very appreciative of your presentation and taking the extra time to answer their questions. If you would like more information about O'Reilly or check out Alicia's book on the learning platform, we will send you an email with a link to that, as well as an email to the recording for today's session. Elecia, thank you so much once again. Have a great rest of your day.
Thank you for coming, everyone.
Bye-bye now.